In this section, we're going to talk about energy that is released or absorbed in chemical and physical changes. We're going to call this section thermochemistry. Thermochemistry is the study of changes that are accompanying chemical reactions and phase changes. Think of the universe as being two parts, the system and the surroundings. The system is the part that contains the reaction or the physical process, and everything around it is considered the surroundings. Energy is defined as the ability to do work or transfer heat energy. There are two types of energy, potential energy and kinetic. Potential energy is abbreviated PE, and it is the energy at rest due to the position of an object. Standing at the top of a stairwell, you would have more potential energy than if you were standing at the bottom of the stairwell, and that's because gravity can pull you down farther due to the higher placement. In a chemical, the potential energy is found and stored within the bonds of the substance. The second type is kinetic energy, abbreviated KE. It is the energy of the motion of the particles in a substance. It's also directly proportional to temperature. In the Kelvin scale, that is a new scale for you. It is different than the Celsius or the Fahrenheit scale, and we will talk a little bit more about it at a later date. So as temperature increases, kinetic energy also increases. Just like mass, energy is conserved. The law of conservation of energy states that energy is neither created nor destroyed, just changed in form. Take a look at the example in the middle of the page. This is a combustion reaction. Octane gas is burning in the presence of oxygen to produce water and carbon dioxide. When the bonds break in the octane and the oxygen to reform into water and carbon dioxide, the stored potential energy of the bonds convert to work and heat energy. This is an example of an exothermic reaction. Both work and heat are part of your definition of energy. An exothermic reaction is one where the system releases energy into the surroundings. Remember that the system is the reaction itself or the phase change, and energy will flow out of the reaction into the surroundings and get warmer. Generally, a thermometer is placed in the surroundings, and you will see that the temperature will increase. Delta H is a symbol used to represent the enthalpy of a substance, and enthalpy is just a fancy word for the heat of the substance. In a reaction, when the heat of the products is less than the heat of the reactants, that will determine a negative delta H, and that will then allow you to identify the reaction as exothermic. If you take a look at the example below, we have iron reacting with oxygen to produce iron 3 oxide. You'll notice that there is a value of energy as a product, 1,625 kilojoules. That is the energy that is going to be released or produced during this synthesis reaction. Another way to write it would be to, instead of including the exact magnitude of the heat as a product, to just go ahead and off to the side of the reaction, usually off to the right, to put delta H is equal to negative 1625. Remember that the negative sign just tells you that energy is being released into the surroundings. The opposite of an exothermic reaction is an endothermic reaction. This is one where the system will absorb energy from the surroundings. Heat will actually flow into the reaction from the surroundings. So remember, the thermometer is usually in the surroundings, and you will find that the temperature will decrease because energy is moving into the reaction. If we look at our delta H value again, change in enthalpy, we will find out that when the enthalpy of the products, the heat of the products, is greater than the heat of the reactants, it will produce a positive delta H. That will be your way of determining that the reaction is endothermic and that energy is moving into the reaction. Take a look at the reaction below. You will see that this time the exact amount of energy This time being absorbed in the reaction is 27 kilojoules. It is on the left-hand side. And basically this reaction is saying that when ammonium nitrate dissolves, it will produce the ammonium and the nitrate ion. This requires 27 kilojoules of energy. Another way to write that would be to not include it as a reactant and to just include the delta H to the right of the reaction with a positive 27 kilojoules. Remember that positive, it means that the energy is being absorbed from the surroundings into the system. On the page you can see two graphs called reaction coordinates. The graph on the left is an exothermic reaction, and the graph on the right is an endothermic reaction. We need to label a couple of pieces on this graph to understand why one is considered exothermic and the other is endothermic. In every reaction pathway that you look at, the reactant will always be on the left, and it will proceed in a curve-like manner to produce products. So we'll label that on both graphs. The reactants are on the left, the products are on the right. Just as if you were to look at a chemical reaction. Reactants, starting substances, make products. The reaction on the left is a downhill graph. You can see that the products are lower in enthalpy than the reactants are. If I was to do a calculation of delta H, where I'm going to take the enthalpy of my products and subtract the enthalpy of my reactants. If I made up some numbers, let's say this was at 10 and this was at 20 joules of energy. If I subtracted my product energy minus my reactant energy, I would get a negative delta H value. Remember from the last slide that a negative delta H signals an exothermic reaction. On the other graph, if we were to do the same thing, if we were to put some numbers at the reactants, let's say the reactants are 10 this time, and up at the top we have products which would be, say, 30, and I was to calculate the delta H, which is once again the heat of the products minus the heat of the reactants. This time you would see that it is 30 minus 10. That would give you a positive 20 joules for enthalpy. And in the last slide, we talked about a positive delta H referencing an endothermic reaction. Notice that this is an uphill reaction. Now that you can see that the reactants have to gain energy in order to get over the hill to produce the products. Another way that we could look at this is that the energy of the reactants is greater than the energy of the products. When the reactant converts to products, it will release that extra amount of energy out into the surroundings. Whereas in an endothermic reaction, the energy of the reactants is lower than the energy of the products. In order for the reactants to form the product, it must find energy in order to get over the hill to make the products. Thus, it is taking energy in from the surroundings and thus endothermic. While on this diagram, I do want to mention a couple of other very important pieces. The first thing that you want to remember is that as we're going from reactants to products, the amount of energy that it takes to get from the reactants to the top of the hill is called activation energy. That is the minimum energy needed to get the reaction to occur. If we take a look at the other side and we draw a line from the reactants up to the top of the hill, once again you will see the activation energy. Notice that this activation is larger than the one on the left. And one of the things that hopefully you've learned by now, or you will learn, is that a smaller activation energy means a faster reaction. A smaller activation energy is going to signal a faster reaction. You also want to label the top of the hill as the activated complex. Or it can be called the transition state. And this is a temporary state in which the reactants have kind of twisted and turned and rotated and have kind of joined together. They're just about to form products, and it's kind of like that intermediate piece that forms before they break apart and become products. Many people use the words temperature and heat incorrectly, and I want to take a few minutes to talk about the differences between the measurements of temperature and heat. Temperature is measured with a thermometer. It can be measured in the units of Celsius, Fahrenheit, or Kelvin. Celsius is the common temperature that we use in science, but the weatherman will actually use the Fahrenheit scale. And we did mention the Kelvin scale a little while ago, and that will become really important when we get into gas laws. Temperature is basically a measure of the average kinetic energy of the molecules in a substance. So the hotter a substance is, the more kinetic energy that substance has. So temperature is a measure of the motions of the molecules, or how hot or cold something is. On the other hand, heat is measured with an instrument called the calorimeter, and heat has the units of calories or joules. Heat is the total amount of energy in a substance, and it is a form of energy that is transferred between objects of different temperatures. Heat energy always transfers from hot to cold, and it depends on three things. It depends on the amount of the substance, so mass in grams, the temperature of the substance and its temperature change, delta T. Delta T would be taking the final temperature minus the initial temperature. And of course the temperature would be in Celsius, most likely. And the type of material. Every substance in this world can absorb heat to various degrees. As mentioned, calories and joules are units of heat energy. A calorie is defined as the amount of heat energy needed to raise the temperature of 1 gram of water by 1 degree substance. Its relationship to the joule, which is now the more common unit to use, is 1 calorie is equal to 4.184 joules. Let me give you an interesting factoid. We know all food contains calories. Well, those calories are actually the big C calories, which are equal to kilocalories. And you learned in the metric system that kilo means 1,000. So 1 big calorie on a food item is equivalent to 1 kilocalorie, and that's equivalent to 1,000 calories. So how did they come up with these numbers? Well, they burned your food. That's what happens in calorimetry. All substances are burned, and they measure the amount of energy that is released when they burn a particular sample of that food or substance. So remember, temperature and heat are not the same thing. Let's take a look at this last diagram, and hopefully you'll get it. You have a cup of coffee that is 90 degrees Celsius, that is its temperature. And then you have a bathtub whose water is 40 degrees Celsius. So we would definitely say that you have a hotter cup of coffee than you do a bathtub of water. Okay, just based on the average kinetic energy of the molecules. However, there is so much more sample of water in the bathtub than there is in this cup that there will be greater thermal energy in the bathtub. There will be more heat coming off of the bathtub than there would be in the coffee cup.